So we'll go with the recording of Jenny Wagner talk, and then hopefully Dan could present, and then we'll finish with the final talk. Okay? So next talk then would be by Jenny Wagner. Well, from the gravitygrinchblogspot.com. Is that correct?
Yes.
Okay. So use data, not models. Lensing of 69 as an example for data-driven inference. So thank you, and go.
Bonjour à tout le monde in the literal sense. Welcome to my talk, in which I would like to give an example for data-driven problem solving and the potential role of machine learning in this inference process. Artificial intelligence has had its ups and its downs. On the one hand, we as human beings are able to create machines that beat the best Go players in the world. On the other hand, we can also build machines which confuse racing cars with the laziest animals on the planet. So despite its successes, artificial intelligence still requires a lot more human understanding of model building in order to make the system more robust and to overcome the failures. Why would you care for anything that I have to say on this topic? Well, I started out in particle physics, where I applied machine learning and pattern recognition algorithms to obtain my master's degree at CERN. Afterwards, I moved on and studied image processing and convex optimization theory in order to obtain my PhD for an application in life science. Today, I'm happily working in cosmology, and I'm particularly interested in strong gravitational lensing phenomena in order to learn something about the dark matter distribution in our galaxy clusters or galaxy scale lenses, and to probe cosmology. I'm using singularity theory and mathematical theorems. So you can now ask, where's the happy end for machine learning in this talk? Wait until the end, because first I would like to now show you how far we can get in strong gravitational lensing without using any lens model, meaning any assumption about the overall deflecting mass density distribution at all. So we don't use any machine learning based model, nor do we use any Bonjour à tout le monde in the literal sense. Take a look at this nice galaxy cluster and take a closer look to find 3 multiple images coming from the same background galaxy. This configuration here is called Hamilton's object. And it's basically everything that we find in terms of strong gravitational lensing signals in the entire galaxy cluster here. So the data is way too sparse to fit a global model in order to infer the global dark matter distribution or the total distribution of mass in this galaxy cluster. The only thing we can do here is restrict ourselves to the vicinity of these multiple images and try to see what local lens properties we can infer from these data sets. Reason number 2, model fits are not always necessary. Take a look at this James Webb Space Telescope simulation pursued by Agniva Ghosh and colleagues. They estimate that we will expect about 1,000 multiple images for one galaxy cluster scale gravitational lens. You can see a forecast here in terms of the multiple images marked by the green dots. So here, the data covers most of the area of interest. We do not need a model assumption to reconstruct the overall deflecting mass density. We can simply use the information contained in the multiple images and interpolate between these images because they lie closely together. Let's now come to the regime where the data is abundant enough to constrain a lens model, but where the data is still sparse enough that we cannot use it as the sole reconstruction tool. A good example here is the galaxy cluster CL0024. You can see it on the left. Here we have a lot of multiple image systems so that we can set up a lens model-based mass density reconstruction. My colleagues and I, we used two different algorithms, namely lens tool, shown in the center, and Grail, shown on the right. As you can see, the mass densities predicted by these two model fits are completely different on the overall scale. So the model fits that we have to the data explain the data equally well, but they are not unique in the overall lens reconstruction here. And which algorithm comes closest to reality, we cannot determine this. We may only get an average idea when we do statistics. But for this particular example, we have non-unique model fitting, and both models do equally well on the data set. So let's go one step backward and take a look at the local lens properties that we get in the vicinity of the multiple images marked by the red dots here. We find that both algorithms have the same local lens properties at the position of these multiple images. So the observables that we have constrain local lens properties that are the same for all lens models. This is the maximum information in which all lens models agree upon. And this is my point that I'm interested in. Namely, I would like to know what local properties at the positions of the multiple images can we infer directly from these observables, and what does this tell us about the gravitational lens? So we want to split the entire lensing region into the positions where we have information and into the rest of the regime where we need lens models to make predictions of what the overall mass density is there. So let's take a look at the strong gravitational lensing formalism again and go back to it to use data and plot models. My colleagues and I, we have developed two different tools. The first one is to take extended multiple images and set up an observable transformation between these images in the image plane. And this is equivalent to a product of local distorting properties of these multiple image positions. So we can get from this tool the local distorting properties of the gravitational lens at the positions of these multiple images. For experts, this is the amplitude and the direction of the reduced shears. And we also get ratios of mass densities at the different image positions. When we take a look at Hamilton's object and we determine these reduced shear directions, we find that these reduced shear directions can be used to constrain the position of the cluster center, which is marked here by the blue circle. And this lensing-based cluster center can now be compared to the cluster center, which has been determined by RedMapper based on a red sequence. So we get an overall rough estimate of the structure which is causing these multiple images without assuming any model assumption, any lens model of this overall structure. The second tool that we have developed reconstructs the critical curve between multiple images and allows us to get an estimate on the smoothness scale of dark matter. Take a look at these two multiple images which mirror each other. We can use these individual features which correspond to each other to reconstruct the critical curve between these two multiple images. And the fact that all 7 images allow for a linear approximation here shows us that the dark matter must be smooth on the scale of the extension of this multiple image pair, which is about 1 arcsecond here. And this has been obtained without using any lens model assumption. We can also reconstruct the source, but only the relative source morphology up to an overall scale. Yet this is possible even again without using any lens model and any assumption about the overall deflecting mass density profile. So let's summarize where we can exploit the local lens properties directly based on the data. This is certainly true in the regime where we only have sparse information, where we cannot fit any model. And we can also use the local lens properties jointly with some interpolations to reconstruct a global lens when we have enough of these local data. The regime in between is the most interesting one, because there we can join the data-based information that we have and the model predictions that we can get, for instance, from machine learning approaches or from human-based models. And when we take this hybrid approach, we can separate the data-based evidence from the model assumptions. And this gives us a highly flexible and efficient new approach, because the local lens properties are common to all models. So just having models in the regions where we do not have data allows us to simply update model predictions by evidence-based information as soon as we get new data. So far, we have to rerun the entire modeling process just because we get new data for the same galaxy cluster. And this hybrid approach would allow to simply update the regions devoid of data as soon as we get an update on the data set. And I think that this is a very good idea to save a lot of runtime, save a lot of memory, and quickly get to the results that we're interested in. If you're interested in the details of the approach, have a look at my homepage. And I'm also on Slack and happy to discuss how we could make progress on this approach. Thank you very much for your attention, and I'm very much looking forward to vivid discussions.
Thank you. Do we have any questions for Jenny? Yes, I see someone in the audience. Neil.
Hello. So it's Niall Jeffrey, by the way. So I wanted to question when you say there are no model assumptions. For example, when just taking an example, you say that when the data are not very sparse, you don't need a model because you can just interpolate, for example. But I would say that itself is a model. Perhaps it's a disagreement of terminology, but to me that would be a model, but perhaps weakly informative compared to a highly informative physical model.
Yes, definitely. So we have a degree of model assumptions, and I think that interpolations are just a very general kind of models, which I would not call a physical model as you defined. And what I mean is we do not need a special physical model in order to make these predictions about local lens properties.
Thank you. Any other question? Yes.
Hi, this is Johannes Buchner. I was wondering how you would obtain uncertainties on the results.
We already have uncertainties on the results, because what we are doing is we are marking these corresponding features with respect to each other in all the multiple images. And they already have a certain uncertainty because we have measurement uncertainties, and we propagate this through the entire algorithm so that we in the end get uncertainties on our local lens properties.
Thank you. Yeah, we have time for one last question. Please say your name before asking the question.
Hello, I'm Thorsten Enslin. You probably said it, but I missed it. How do you represent these mappings? So mathematically or
Mathematically, it's just an affine transformation. So you have the shear distortions, and you have the convergence, which is just a scaling.
Okay, so you're not using a neural network in order to represent them, but you're basically expanding a metric. Thank you.
Yes.
Okay, thank you very much. Let's thank Jenny again. And
thanks a lot.